Hi there, this is session 19 of programming from the very basics using Python. In this session, we will learn all that you need to know about a tuple. So all the aspects of a tuple, and also very important part of this session will be focused on covering the concept of immutability. We already learned how to create a tuple in the earlier sessions. I will go a little more, one more layer deep into it, and I will tell you about what makes immutable objects and why objects are immutable. And also, if time permits, I will talk about hashability of objects. Now, if you know from the earlier sessions that we can always create a tuple by the act of tuple packing as the most easiest way, you can actually use A is equal to, or I can use T. T is equal to, and I can try out something like say 10, 20, 30. Okay, I didn't select the kernel. Just a moment, please. I will actually have to select this. Okay. So I type T is equal to 10, 20, 30. And if I try to print T and type of T, you can see very well that it's a tuple. Well, when you print a tuple, it shows up in parentheses. That's the official way tuples are represented literally. But in this case, parentheses might not really be useful. Not really required. It's not useful. It's not really required. But if you prefer to use parentheses, you can go ahead and do it. There's nothing wrong in it. You can always use it like this to explicitly mean that you're creating a tuple. No problem. No difference at all. You might need to use parentheses if you're trying to create tuple and also add in some expressions. For example, I am not sure if I covered this. If I try something like this, if I say 10, 20, 30, and if I just say into 3, for example, this will end up creating a tuple that looks like this, where this 30 into 3 is first evaluated as an expression, and then tuple is created based on comma separation. The tuple creation, if you take it as an expression to create a tuple, has a lowest precedence compared to arithmetic expressions or even comparison expressions as such. So in case you want to, let's say, scope this, in this case, where you want to create a tuple which must be repeated 3 times, you can always use parentheses in here to scope it. This way parentheses might be useful. If you're going to be using a tuple or creating a tuple, which could be a part of another expression, then you need explicit parentheses. It's also a case where you're passing arguments to functions. So if at all I have a function that accepts a tuple as an argument, you need to explicitly use parentheses to represent the tuple. Let me just detour and show you that. So if we just create a simple function, let's call this function as, I'll call it test fn to indicate test function. Fn is generally a shortened name to say functions in most programming languages as such. So you could use that name if you want to. So I'm just trying to indicate this function does nothing else. So it's a very simple function. So here in this test fn, if I want to take a tuple as an argument and call it t, you can see that in the function prototype, there's no hint about what type of argument you can pass. There is support for type hinting. It's a digression, sorry. There's a support for type hinting in Python, which was introduced in very early versions of Python. I'm not sure whether it started from Python 3 or Python 4. Python 3.3 or 3.4. So one of these minor versions, 3.3 or 3.4, sometime during the time, the concept of type annotations and type hinting made its way. It has become quite mature at this moment, and there's a very rich type hinting support in Python. I'll talk about that when I talk about function prototypes in a dedicated session. For now, I'm not using type hinting. I'm just using a t here. So when you just pass, when you say an argument is t, you can't indicate whether it's a tuple or a number or whatever. So let's assume that it's going to be a tuple and it has to, let's say, iterate over each of these elements. Let's say total equals 0. And say for v in total, and if I just try to print v, right? Maybe I just say maybe total plus equal. Sorry, not total. Made a mistake. V in t. Total plus is equal to t. And maybe this returns a total sum of all numbers in a tuple. Let's assume that. There's a simple function I created. Now, if I call test fn, if I just put 10, 20, 30 like this will throw an error. And whenever you call a function with wrong parameters, if a function takes one argument, but you pass 3 arguments, function expects 3 arguments, but you just pass a fewer number of them, or so on. if the number of arguments don't match as per the function prototype, then normally you'll get a type error with the actual message here. So it shows a type error with this particular line. It shows type error. Test fn takes one positional argument, but 3 were given. Now try to treat this 10 as one argument, 20 as one argument, and 30 as one argument. For taking 3 different arguments, the function must have 3 different variables added in here. Like say, t, comma, u, comma, v, or a, comma, b, comma, c, whatever. You need to have 3 arguments. Only then this function works. But how do I tell this function that I'm passing one argument, but that's a tuple? This is where you might need to use explicit parenthesis to make it work. Let me just copy this cell and show you what really works here. So to call this, you need to pass it on like this. This is where the parenthesis for the tuple is required because it's part of an expression. That's a function call, right? So when you run it now, it throws something else. I think it's a bug in my program here. Okay, total plus equal to t. Okay, I made a mistake. Logical error, sorry. It's a typo. Anyways, I'll fix that even here. Though this still won't not work. But you can see that here, I'm just trying to accumulate each value in t into total. And you don't have to worry about the function arguments, function's body right now, but that's irrelevant. But what is really important is how I'm passing a tuple as one single argument to a function. I need to use parenthesis in this case, right? So you can see that. You might ask me, should I really pass a tuple? Can I pass a list? Can I pass a set? Yeah, this function will work. This function is super flexible. You can see that. I can actually pass a list and it will still work. Right? So it is still working. So you can see that. What if I pass a string? Will it work with a string? Let's try. THE, for example. It throws an error here because total is 0. You cannot accumulate t with a 0. You cannot add to t with a 0. So there are some issues that you can see. So that's where type hinting is mostly useful to make your function prototype look more explicit to your user who's going to use your function. We'll worry about that in another session. But now let's go back to a tuple. I told you how you can create a tuple literally by using parentheses if you want, or just comma separated items in the right hand side expression, which returns a tuple. There are also another way to create a tuple that you might have already learned in the earlier sessions using the constructor expression. Let me put them all together. So there are 3 primary ways to create a tuple. Option 1 is literal notation, which is typing t is equal to, you could use 10, 20, 30. There's one way to create it. And there's another way to create a tuple, which is also called as constructor expression. If you have an iterable and you want to create a tuple from it, we already learned that you can always use tuple constructor and pass any iterable as its arguments. This time, let me pass a string. We just type hello. And if I try to print t, type of t to confirm it's a tuple, right? You can see that. And this is another way to create a tuple. You can see that strings are iterable objects. You can iterate over each items of a string or each letters in a string, right? So if you pass that as an argument to a tuple, the tuple constructor will iterate over each item of the iterable and stores them as separate items or individual items in a tuple. So you can see a tuple that seems to be sort of, what do you call, exploded, they call them, right? So it's a string is exploded into individual characters, like individual bits, and collected into a tuple. Here's an interesting trivia. What if I want to convert this back to a string? Using tuple constructor, when I pass a string, I get a tuple. If I want to, let's say, create a string back from this, you might think, oh, can I not just do a s is equal to str of t? Will this work? Can I create a string from a tuple like this? Let's try and find out. Whoops, it didn't. Is this a tuple? No, it's a string. It is a string. It looks like a tuple, but let me tell you, the type of s is string. Basically what it did is, if you try to print this directly in a REPL, you'll know the reality. You can see that open quotes, parenthesis, in single quotes h, comma, single quotes e. It's like asking, when you use str function, str construct, pass any argument to it. The str just sort of queries the object. It's like, it's asked the object, as a string, what are you? Or it's like a very simplest forms of asking, who are you? And the tuple object reports itself. T is a tuple. It reports itself saying, I'm a tuple. To say I'm a tuple, open parenthesis. And then string representation of first object in this case is a string, so it's in quotes, comma. String representation of second object, again it's a string, it's in quotes, comma. It goes on till all the elements, then close parenthesis. So most objects have their own string representation, and tuple is shown up as string representation when you get it. How do you get back the original string hello from a tuple like this? Think. Any guess? Well, if you got the answer, I guess you know what it is. Previous session, I talked about the join method on a string, isn't it? It's a iterable of strings right now. Though it's all string of single characters, you can always get back the original tuple by using this trick. You can just try double quotes dot join of t instead. You explode a tuple. It's like you explode a string, exploded a string, split it all into individual bits in a tuple. You combine them back, or glue them back to a string by using the join method. Like this, one of the ways you can interchange it. Let's go back to the previous. I told you that you can create a tuple using the literal notation, using constructor expression where you use a tuple constructor, pass any iterable. It can be a list, it can be a string, it can be a range object, enumerate, zip, all of them, right? All iterables can be passed as its argument. It creates a tuple by iterating over each of those items. The next one is a very interesting one, which I will put in a separate cell mode, but I will just perform to show you formally. I just keep them in the same cell. The other form of creating a tuple, which is applicable even to a list, set, and even dictionaries, is using what we call as comprehension. Let's call this as tuple comprehension. And tuple comprehension comes in two flavors. At this moment, I'm going to show you just one of them. What is comprehension? Creating a collection, like a tuple in this case, using an expression. Wow, what is that expression? Not a constructor. It does construct a tuple, of course, but it uses much more than just constructing it. For example, let's say I use t is equal to range of 10. Oh, r is equal to range of 10. Let's call this r to indicate it's a range object. If you try to print r, it shows a range object. No doubt, range is a construct which creates a range object in Python 3. Now, if you want to create a tuple from this, you could actually do this. You could actually use t is equal to create a tuple from this range, right? So range is an iterable. The range constructor returns an iterable of 0 to 9, right? And you can construct a tuple iterating over 0 to 9, and you get what you really wanted, like say t. But now the problem statement can get a little more sophisticated, where I would say, I just don't want numbers 0 to 9. I want squares of numbers. I want 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. Wow. I can remember squares of first 10 numbers. Nice. All right. I want to get squares of numbers, the first 10 numbers. How do I do that? I want to create a tuple of squares of first 10 numbers. Oh, you can't do it with range. You might be able to pass step value if you want. That will not give you squares. You'll just skip some of the items. That's it, right? So one of the ways you can do that is by using what we call as tuple comprehension. How do you do this? This might require careful observation. So if you want to take some time off, just observe what I'm doing here and then try it out. So you would say v into v for v in range of 10. You can see that it looks like a ingredients of a for loop, isn't it? This is an expression, not a for loop. The relation between this expression versus the actual for loop, which I talked about in the previous sessions, is similar to using the if condition block, if statements, versus the ternary if expression. What do you see there? The same keywords are reused. And they sort of work similarly. Both are used for checking conditions, One of them is for simple use cases. Another one is for more sophisticated use case, the if statement. So when you want to write a for loop where you want to just create a collection with items in it by iterating over another iterable, by applying a simple expression, you can use comprehension as a shorthand. It's an expression. You can use it in right hand side. So what you're trying to say here is that create a tuple, the tuple constructor, create a tuple which has value into value. I'm just calling value, it's actually v into v, for each item that's v in range of 10. So for v in range of 10, what does it do? V will be equal to 0, then v is 1, then v is 2, then v is 3. But what I want to store in a tuple is not v, but I want to store v into v. And that will give you a tuple of squares of numbers. This is very interesting because this is also a feature that actually makes a lot of your code more succinct, more simple, more elegant the moment you know how to use it. I think I saw this kind of a comprehension expression first arriving in Python. I think Python is the first language where I was introduced to this. I'm yet to see this in many other languages, but slowly some other languages, I think I saw that also sort of partially implemented in Scala, and I heard even Haskell has something like that, and different languages, right? They have slowly inculcated that. I heard JavaScript 1.7 also has something called array comprehensions. Not very popular, but they say, oh, it's there in Python, so let's use it. But nobody uses them, so that's what it is. But Python, you use this very extensively. This is a map transformation. It's a map function. Actually, it does what a map function does. Map is a mathematical concept, mostly covered in set theory. You have an input data set, which has got a lot of entries in it, a lot of numbers in it, let's say a lot of data. Each of those items in that set, you want to transform them to a result set, one-to-one transformation, using a single expression. Right? So this is called as a map function. So the input data set and the output data set will have equal length, and 0 becomes 0, 1 becomes 1, 2 becomes 4, 3 becomes 9, 4 becomes 16. So it's a one-to-one transformation. Because it's like a one-to-one transformation, it's also called as a map. Right? So this is a tuple comprehension applying a map operation. I'll not call it map function. There's a function called map in Python. Therefore, legacy reasons, perhaps there are some use cases where map is suitable, but comprehensions are the way you can do something like this. So basically, range returns a range of numbers from 0 to 9, but I want to transform all those numbers one-to-one, where 0 becomes 0, 1 becomes 1, 2 becomes 4, 3 becomes 9. So it's a one-to-one transformation of all the items, and that you apply using a comprehension expression like this. And you can do wonders with this once you know how to use it. Let me show you another one. Let us say that I have one set of numbers. Let's call this A for now. Keep it simple. Is a tuple of numbers like, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I could have created this using range, but I'll do one thing. I'll make it random. I'll scramble it a bit. Okay. I'll say 4, then 8, then 12, then maybe 18, then 6, then 5. Right. And then I have B, which is another series of numbers, which are also sort of random. Let's use 2, then let's say 9, then 5, then 16, then 4, and maybe 3. As you can see that these are two tuples which are already created, literally, right? And we can print that. You can just say A and B, they're two different tuples. What I really want to do is that I want to create a new tuple, which is C, where I want each item of C to be the sum of the items of A and B. Like what I really want is C should contain the first item as 4 plus 2, Then second item as 8 plus 9. Third item as 12 plus 5. Then 18 plus 16. Then 6 plus 4. Then 5 plus 3. You know what I'm trying to do? I want to add each of the items of these two tuples and create another tuple, which is like the sum of each items of the two tuples. How do I do that? Well, some of you who come from other programming background will think, oh yeah, loops and conditions and whatever, like, it's like some kind of code logic. Python, one-liner. How? Here's what I can do. I can just try C is equal to create a new tuple which stores x plus y. X plus y. You want to find the sum of it. And where is x and y coming from? For x comma y. And in what? In what? So how do you complete this? Fill in the blanks. What do you do here? You want to parallelly iterate over A and B. So you'll do a zip of A comma B. And now when you try to print C, just see what you get. Voila, I got the answer. So you can see that 4 plus 2, 6, 8 plus 9, 17, and 12 plus 5. So, yeah, 12 plus 5 is also 17. Yeah, 17. 18 plus 16, I will believe is 34. Yeah, it is 34. 16 plus 16 is 32. Yeah, 18 is two numbers extra, so 34. All right. 6 plus 4 is 10, and 5 plus 3 is 8. You can do that very nicely. Can also be applied to strings. So let's try this. Let's say we have two strings here. Let's say we have first names in one collection. First names are, maybe let's use John, Tim, Tom, and Peter. And let's say last names are Doe, Jones. What do I think now? What are the last names? 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 Smith, whatever. And then say Williams. And now I want to create a string. I want to create a collection which has got the first name and last name put together. So names is equal to create a tuple of, I could just use concatenation here, isn't it? Yeah, we can just use F plus space plus L. I want the first name and last name with spaces. But you know what? You can do it like this, but yeah, let it be. I will show you how to improvise. I'll tell you how to make it even better. For F comma L in zip of first names and last names. Oh yeah, I forgot to print names yet. Let me print them. We got it. One other level to improvise this is obviously whenever I see code like this, basically I want to just create a new string which has got all these things, concatenation, all these, right? So you can make it even more shorter. What I can do is I go say tuple of F string. Ultimately, I want a string, right? Which contains the first name followed by the last name. You got the same result. Lesser keystrokes to type. We can also do something more wonderful when I do this. Maybe I want to capitalize these names. So I can use F dot capitalize. I want to even capitalize the last name. So last name dot capitalize. When you have a line that grows long like this, long in a comprehension expression, it's a good idea to continue the next line, but you cannot just put enter like this. It's a syntax error. Let's see if it works. Well, it actually worked. In this case, it's easily tokenizable, but certain times you need to put a backslash at the end and continue. Okay, this is fine. You can always continue the next line like this. So you can see that it comes out very nicely. And you can see how you can use comprehensions or tuple comprehensions to create a tuple by transforming items of an existing iterables, right? The syntax grammar, again, let me recap this, is always what you want to store in a tuple. What is the result that you want to store in a tuple? The resultant expression, the outcome of a result, outcome of an expression that you want to store in a tuple for elements in iterable. That's how you see it as. This is also called as a mapping transformation or mapping comprehension, I could call it. These are not like the official terms. I'm just making it up, by the way. So it's a tuple comprehension applying map operation. But sometimes you want to do filter, which is where things are even more interesting. So let's assume that I have a tuple. Let me create this cell below. I have some existing numbers which have a lot of entries in here: 45, 32, 78, 12, 92, 13, 17, 18. I'm trying to make it as random as I can. So 23 and 27, then 48. Okay, it's fine. I think this number should be good enough, which is quite random enough for me. Now what I want to do is that I want to extract all those numbers. I want to extract all those numbers which are less than 30 from here. All values is less than 30. I want to extract it. Everything that's greater than 30, I want to just leave that. This is a filtering operation. I'm filtering out elements of an existing collection or a data set to my liking based on some expression. You can do that very elegantly using comprehensions as such. And here's a tuple comprehension example. Applying a filter. Last time I applied a map. This time I'm applying a filter. We just type t is equal to create a new tuple where I want n for n in numbers. And I'll try to print t. It's nothing. It's just, you could have simply said tuple of numbers as it is. But when I do this, it's like telling each value for value in existing iterable, in this case tuples. But now I'm going to add a condition here by using if n is less than 30. You see what I did here? So this is an optional clause that you can use when I'm constructing a tuple this way, using comprehensions, that is, where while I'm iterating over every item of an iterable, I can say store this value only if this condition is met. And when I do that, you can see the result. We got a filtered tuple. Oh, the filters will give you, it's like it gives you super, it'll give you superpower. I'll say superhuman powers, whatever, right? So I can just say, you can do wonders with it. All kinds of conditions can be applied, all kinds of conditions. We can chain load conditions. You can actually say, if n is greater than 30 and n percentage 2 double equal to 0, give me all the even numbers which is below 30. That's great. We can apply it in all use cases. I found this also very useful in weeding out things that you don't want. For example, let me show you a realistic scenario again. Let's try this. Let's say I have some data set, which is pretty much like this. D is equal to, I have some strings. Some random strings. But unfortunately, there are some numbers in it. Numbers. I say 56, and there's also another string, let's say world, and maybe 5.2, comma, and I have something else. Maybe I could have a none object. I could have something else. I could have different kinds of other arbitrary objects, which are like noise for me. And I have some strings. Let's say maybe anything else. I can just say, okay, I'll just test one more time. No problem. What I want to do is that I want to join this. Can I use join method to join this? Let's try. Comma, dot join of D. Whoops. Failed. And you know why? Because join expects that you pass an iterable that only gives you strings and nothing else. It will not work if it finds some data that's not a string. You're left with two choices. One, transform all the data which are not strings to a string and then join them. That's one option. Or maybe filter them out. I'll show you both options here. So here, I can use a comprehension expression directly. This is really not tuple comprehension per se. Whatever expression, really, the comprehension can be used in many functions or any expressions which expects an iterable. So a join argument, it expects to be an iterable. You can dynamically construct some kind of a collection or a tuple, maybe you can say that, by directly passing on a comprehension expression. It does not create a tuple, but it's a comprehension expression that can substitute the argument if an argument is an iterable for a function or any expression. So I'll show you that here. If I can just type join of v for v in d like this. Obviously, it's not going to work. Still, it's the same error. But what if I do this? Str of v. Explicitly try to represent everything as a string. If it's a string, it'll remain a string. If it's a number, it'll get converted to string. None also has a string representation. Then you can see the outcome of it. Well, it works. This is sometimes a very practical use case scenario. I found this quite useful in production code when you're dealing with some data and for debugging purpose or any other use case. Maybe sometimes you want to store the data in string format, stringified format in somewhere, like maybe in a database or maybe in some file or anything as such, right? Sometimes you deal with data which are not strings, but you can stringify them, each of these items, by applying this kind of a expression, right? So here's an example of using comprehension expressions as an argument to a method, or it can be also a function which takes an iterable, which expects an iterable. So I'll write a comment in here. In most cases, I can't be sure that it'll work in all cases. There are some badly, also rigidly written functions, not in the standard library but outside it, which expects a tuple. And if you don't pass a tuple, it'll just say, I didn't get a tuple. It may not work with its kind of expressions. But in most cases in Python, a comprehension can be used in places where an expression like a function call expects one of their arguments as an iterable. You could do that. It's a very interesting one. But maybe you don't want to, convert everything to a string and print it, but maybe you can also do this. I'll just use print to print the output of this. So you can store in a variable, but I'm just going to print it off right away. But maybe I can also do it another way where I can filter it. I want to use comma dot join of v for v in d. I can use if type of v is str. This is another form. Interesting. Another interesting one. What is this? What is this expression? I'll tell you. You can always find out type of any object, right? If you just have a is equal to 10 and say type of a, what does it tell you? It returns an integer. How do you programmatically verify whether an object is of a given type, specifically a given type? If you want to do that, you can use type of whatever argument you pass here, and you can simply use is integer. This is one way to check for specific types, objects being of specific types. There's also another built-in function called isInstance that uses what we call as the generalization rules. It works very well with this Liskov substitution principle. See object-oriented term. Okay, so I'll get into that right now. But you don't need that in this case. If you want to look for an object to be of a specific type, you can use this. If you want to use generalization, then maybe you want to try out other forms as such. So I want to ensure that a is an integer, I can use type of a is int. If at all a is not an integer, if I just say dot zero like this, it false. Right? Maybe if you want to check whether it's an integer or a float specifically again, either it's integer or float. Maybe you can say type of a is int or type of a is float. Right? Type of a is int or type of a is float. In my opinion, this can be made better. Can make it better. How do you make it better? Well, too much words. Type of a is int or type of a is float. Short away. Type of a in int or float. Type of a returns the type. I'm checking whether the type is in this collection of integer or float. And maybe tomorrow if you want to check for complex, it's easy to just put comma complex here. Compared to using another idiom there where you say type of a is int or type of a is float or type of a is complex or type of a is fraction. Too much to type. But you can make it more simpler just by using this idiom that you see here. As you can see, now your brain is slowly getting rewired to think in the succinct form. If you come all the way here, if you made it through till this point, right? So this is how you use all these ingredients of a program: in operator, is operator. Some of you might ask, why am I using is operator? Why not use double equal to? Here's a rule. If you want to check an object against a singleton, use is operator. Now, I used the word singleton. What exactly is a singleton? Singleton is a popularly used in object-oriented programming, but it's a generic concept. Singletons are objects which don't have any duplicates of themselves. Singletons are objects which don't have any duplicates of themselves. There's just one object called int that represents the integer type. Everything is an object in Python. Even types are objects. Int is an object. Float is an object, right? I think I covered that well enough in the very early sessions. There's only one object that represents a data type for integer. There's one object that represents data type for float, and they're all represented with these identifiers called int, float, complex, and so on. So these are singletons, singleton objects. And thus, because you know that all of these types are represented as singletons, which I just mentioned, if you really want to compare objects, you're not going to be comparing against values. There are no two copies of int in memory, no two copies of type called int in memory. There's only one object called int, right? One object that represents the type int. Rather than using double equal to, it is more apt to use is operator. As we know that is compares whether two operands refer to the same object. So type of a refers to integer type, and int also refers to int. So it's more obvious that you normally use is operator rather than using double equal to operator for the comparison. And that's the reason why I use is rather than equals operator, right? As such. Anyways, so I talked about how you can, create a string by joining them, but when there are some arbitrary values, how to filter them out or how to transform them if necessary to strings. And these are some example use case of comprehension expressions. Now let's come back to tuple again. So when I talked about tuples, I told you how to construct tuples in three primary forms. Little notation, we all saw that. Let's scroll back a bit. Here's where it is. All in one place. The little notation, constructor expression. And then I talked about comprehension, and this is an example of a map, right? But you can also apply a filter by adding an if clause right there. You can also combine map with filter together. You can filter out elements of an existing iterable based on some condition and then transform those filtered elements using any expression. So both can be applied in tandem. So it makes it more convenient to use comprehensions in such cases. rather than using some other functions like map and filter, which I will discuss much later. All right. Now, I told you that you can create a tuple, and tuple is an object, and there should be some methods on it. So what are the methods that a tuple has? Before talking about methods, let me tell you about the operators that tuple has. If you already have gone through string operators, I told you when I talked about string concatenation, string repetition, and subscript operator, I also mentioned that these are standard features available in all sequenced collections. This is even applicable to a tuple. So if you have a tuple like this, say a is equal to 10, 20, 30, and b is equal to 40, 50, 60, you want to concatenate them. You can say c is equal to a plus b, and this would work just fine, as you can see here. So you can see this C is a new tuple which is created by concatenating A and B, right? It's a new tuple that's created here. You can also repeat a tuple, as we just saw some time back. We can always have an existing tuple, and I could say B is equal to A repeated maybe 5 times. And if I just try to print B, you can see that all the elements of A, all the items of A is repeated 5 times in here. So this is another way you can also apply repetition to grow a tuple, repeating elements all over. These are called as sequence concatenation and sequence repetition operators, applicable to all sequenced collections. When I talk about a list, even a list supports all these features, right? The next thing I should also quickly recap is extracting items of a tuple, where let's say I have a tuple of numbers. Let me use some random numbers in here. Let me repeat some numbers because I want to show you some other features too. So I can reuse the same tuple for the example. The numbers are repeated. Some of the numbers are repeated. In fact, oh, well repeated. Okay. So if I try a of colon 5, I guess you know what the answer is. It returns a new tuple, which is a slice of an existing tuple, but only the first 5 elements, right? Which you can see here. So the first 5 items are sliced out into a new tuple, and that new tuple is what you see here, right? You can also try all these things out. I'll just use print to print them. I can get the first 5 items. I can get the last 5 items if I want. Sorry, minus 5 colon. Or if I want to get some parts of the tuple based on start and stop index, I can also do that by using a of maybe 3 colon 6. All of these slicing operations I talked about that are applicable to a string, you can also apply to a tuple. These are common features on all sequence collections. You can also see that you can extract alternate items of a tuple if you want to. You can do that by using a of colon colon 2, for example. And this extracts 45, but not 43, but it takes 67, 29, then 53, then 23, then 43, then 67. You can see the output here, right? It's pretty much obvious. So you can extract elements of a tuple using slices, skipping some of the items based on the step value, which you pass as a third parameter in here. The 2 colons, as you can recollect, means that from the start to finish, because it did not provide the start index, did not provide the stop index, it extracts all over the tuple. But maybe if you want to extract part of a tuple but want to apply some step values in them, you can also do that by using something like a of maybe 2 colon 8 or 2 colon 8 colon 2. Starts from index 2, 2, 3, 4, 5, 6, 7, 8. Amongst all these indices, it tries to, I think it's, have I counted it correctly? I don't know. If I just count it, I think it's like, yeah, it's a 2, 3, 4, 5, 6, 7, 8. Yeah, I think I was correct. From here, it gets the first item from the slice, that's 67 that you see here. Then skips the second item from the slice, that's 89 is skipped. Then you have 21, 23 is skipped. Then you have 53. Then you have 78. And yeah, last index is not inclusive. So obviously the 23 will not be there at the end because stop index is non-inclusive anyways. So you can apply all these kind of slice operations even on a tuple, just like you did on a string, right? And it'll work all just the same way even when you learn how to use a list. All these features are also available in a list data type. But anyways, let's focus on tuple now. What methods are available on a tuple? Well, tuple just has two methods, and these methods might look very obvious to you when I tell you what they are. So we say a dot, you can see that there are two methods. All of these are special attributes and methods, you can ignore them. All the dunder attributes are here. Every object will have them, right? You can ignore that. But you can see there's only count and index that we normally use. So we say a dot count of, let's try maybe 45. How many times 45 occurs? Or you can also find out the first index of a number, let's say 89. I can say a dot index of 89. These are pretty much like how it worked on a string. And yes, in the index method on a tuple, will also raise an exception if a given item is not found. So that is something that you should know about. So you need to use a try except block. There's no find equivalent in a tuple. You have only index, right? So you have count and index are the only two methods that you have on a tuple. Now comes to the concept of immutability. A tuple is an immutable object. When I say what I mean by that, so if I just try this, if I just say a is equal to 10, 20, 30. Once a tuple is created, you cannot change their items. You cannot alter their items. You cannot like say change the first item to 100 or add a new item on an existing tuple. Whatever you do to a tuple, all kinds of transformation, all kinds of changes, you can only do so by creating a new tuple. You can only create a new tuple when you're altering changes. I'm not sure if you have a tuple like this and you want to make, say, create a new tuple where I want 10 to be altered to 15 while retaining all the other elements of a tuple. You could just do this. You could say b is equal to create a new tuple where I want to make sure that, this can be a little trickier. Because in this case, if you know that 10 is the unique number, you can do it very easily. You can do it if you can say v plus, you can just say v plus 15 if v equals 10, else v for v in a. Yeah, I know it's a little complicated, but yeah, this is how we do it. Oh, not plus is 15. I can say 50. I want to replace 10 to 15, so I can just put 15. This will replace all occurrence of 10 to 15 in a new tuple. How does it work? Why did I put if here? Well, I'll tell you. This is an expression. And what do you see here? It's a ternary if expression. So what I want to store is a result of a ternary if expression now. Not v plus v, v into v or anything as such, which I did a simple use case there, right? So here I'm trying to say store 15 if v equals 10, else store v as is for v in a. Or remember, when I put an if clause after the for construct, which you see here, it is a filter. And this is not a filter because I put the ternary expression here. That means there's a one-to-one mapping. 10 becomes 15, 20 remains as 20, 30 remains as 30. So you want to do this cherry picking of items and then transform certain items alone in the final destination, in the final tuple. Why did I use final destination? Looks like a movie, right? Yeah, the final tuple. So in the final tuple, then you can actually use the ternary if as a workaround. And this is another idiom that's quite popularly used in transformation, right? In using comprehensions to transform data from the source. But you can see that you have to end up creating a new tuple. You cannot alter an existing tuple. Some of you might ask me, what happens if I do this? If I have an existing tuple a is equal to 10, 20, 30, and if I try to say a of 0 is equal to 100, this is not going to work. You can see the error is quite explicit. It says type error, tuple object does not support item assignment. Once you create a tuple, you cannot add new elements into it. You cannot remove elements from it. You cannot change any elements in it. So it's fixed. It's fixed, right? And an object like this is called as an immutable object. Now let me tell you what are immutable objects in reality as I'll define them. Immutable objects are objects. Let me make this a markdown. Yeah. Whose notion of value cannot be altered after construction, or maybe you can say after they are being created. Basically construction. So immutable objects are objects whose notion of value, you cannot alter that once you create them. What do you mean by that? Every object which represent data, all of these are data types: integer, float, complex, string, tuple, list. They represent data. The data they represent is their value, their notion of value. If you ask a tuple, who are you? It says, I am 10, 20, 30. That's the value. A collection of numbers in this case. So if you cannot alter those values, once you create those objects, such an object is termed as an immutable object. Tuples are not the only immutables, by the way. Though I'm introducing you to this concept of immutability much later, when I'm introducing to tuple, I thought it's too early to cover immutable when I talked about numbers. But let me tell you, most of the data types we have discussed so far, or most of them, are actually immutable. Numbers are immutable. Even numbers, when I say A or B or C and say assign it to a number, let's say if I say A is equal to 100, and this value 100 is immutable. You cannot change this value anymore. Can I not change the value? Well, what if I do this? You might ask me. What if I say A plus equal to 1 and print A, type of A? I changed it. Isn't it? I changed it. Well, you didn't change 100 to 101. You didn't change the value of 100 to 101. A was referring to 100. Now you made A refer to another number which is 101. To understand immutability, I think the best example I can think of is your currency notes, the dollar bills or your rupee notes, which you have it with you. Do I have it with me? Let me just check. Oh, yes, I have it with me here. You can see that. I have a currency note here. It's a Indian 500 rupees note, which is currently there. Can I change this number? It shows 500 here, if you can see that. What if I had another zero here? Can I do that? I don't, it's illegal, right? I cannot just put zeros all over the place and make this 5,000 or remove a zero or make such kind of changes, right? So this is the value that you see here is immutable. This note is printed, it's immutable. How do I make this 500 rupees to maybe 1,000 rupees? I need to borrow another 500 rupees from someone maybe, or maybe earn it, and then I have 1,000 rupees with me. This note, I cannot change it, right? I cannot change this value here. So we see a lot of information in real world which are termed immutable, right? For example, your name is mutable. You can always change your name. You can. Maybe I don't like my name. My name doesn't sound very flashy or very popular, and so I can change my name tomorrow and say my name is Rajnikant. I'm not sure who you. I guess you know who Rajnikant is. He's the very popular superstar in South India. You watch his movies, or I can make some name like that, Shah Rukh Khan, or things like that. You can change your name. It's perfectly legal to change anyone's name. Not anyone's. I mean your name, by the way. Yeah, but I don't think I change your date of birth. Your date of birth cannot be changed. That is immutable. I think I told you it's a constant also, but I'll tell you, constants and immutables are often confused by people. If I have an identifier that points to an object, and if I cannot change this identifier to point to some other object, that identifier is a constant. Constants are kind of identifiers which cannot be adjusted or changed to point to some other value or some other data or some other object in Python. Python doesn't have constants. Officially, no constants. So constants are merely convention in Python. We learned that in the very early sessions. But you have an object in memory. If you cannot change the value of the object, if you cannot change the value of an object, such an object is termed as immutable. Here, let me prove this to you. Let me give a bigger number, let's say 1000 for now, because I have a diagram to show you after a while. I say a is equal to 1000, and I print a, type of a, it's integer. I'm going to print also the object's ID. I guess, every object is uniquely identified by a number, which is the object's ID in C Python. That's the official Python implementation. That's the memory address where the object is residing in. Objects reside in memory, right? All these objects are allocated and represented in RAM, in your memory. So obviously the address in memory where the object resides in, that's what ID returns, right? In your official Python implementation. So if at all I look up ID of A after this, the ID is different, isn't it? Let me show you another example again. Let's say A is equal to 1000 and B is equal to A. We all know that assignments copy references. I think I covered that to great length in my very early sessions. If you skipped it, go back and read my early sessions. Watch my videos in early sessions rather. So session 2, session 3, I will talk about these concepts. So I'm just going to print B and A and B, and I'll also print A and B even here. And this time I'm going to use the F string. I find that very convenient to print it, so it looks very nice, right? So I'm going to just use F string, but I can use A is equal to and B is equal to and ID of A equals and ID of B equals here. I can try the same thing even here. I could use F of A equals B equals. Forgot the quotes here. Sorry. Let me put this quotes. Yep. And ID of A equals. I could just copy that line all over. So okay, I came all the way through till here. So fine, let it be. All right. I created an object representing 1000 and I have an identifier A referring to 1000. The moment I say B is equal to A, what really happens? B refers to same object as A. As a proof, ID of A and ID of B will be the same. That is, B, A and B refer to the same object. But the moment I say A plus equal to 1, and then if the object was indeed mutable, if I could change the number in memory, the contents, right? If 1000 become 1001, when B would have had the same value as 1001, isn't it? Let's try this. Where you can see that A is 1000, B is also 1000. Look at ID of A and ID of B at this moment. They're both the same. They're both the same, isn't it? Let's look at the last numbers. It's like 240 and I can see 240 here. I'll assume that all the previous numbers are identical. Okay, so 240 and 240. So it's same. But the moment I say A plus equal to 1, A now represents a different object. We can see that it's a new ID. Whereas B is still representing an old object. A very diagrammatic way of representing. I think I have the diagram partially ready. So here I have an object representing 1000, which resides in a particular memory address, which I put in a very small numbers here. I hope you can see that, but the same address I've pasted in here. This is a memory address, which is a value. The key of it is a variable name, which is A. And this is in the main module's dictionary, by the way. I think I told you when I talked about modules that all variables that you create, global variables that you create, ultimately are keys in the module's dictionary, and the corresponding values are nothing but the IDs or the memory addresses of the objects they refer to. Right? That's what they are. Now, when I say A is equal to this, I get this value. So I can even have another variable called B. When I say B is equal to A, what really happens is B happens to be another entry in here in this dictionary, and the reference is copied. I told you all assignments copy references. Just a quick recap. And you can see that the same address got copied here, which also means that B also ultimately refers to the same object. The moment you use the expression statement a plus equal to 1, a plus equal to 1, 1 was an object somewhere else in memory, which might have some other ID, of course. Adding 1 with 1000, another object is created, which is a new object whose final result is 1001. Let me adjust that. 1001. And is assigned to A. A plus equal to 1 is as good as telling A equals A plus 1. You're assigning back to A. What does it mean? A no longer points to this location. A points to this address. Let me do one thing. Let me put this A below now, so it looks a little better. Otherwise, it looks very crisscrossed across the arrows. Cross across. It looks very confusing. And the address of this is, what is the number? Let me copy that number here. It's a different address. Let me just increase the font size to match this up. Now we get a picture. You can see that 1001 is a new object, and A is now referring to the new object, which actually means that when you do any kind of arithmetic with numbers, all kinds of arithmetic you do, they end up creating new objects. 1000 plus 1, a new object is created. 1000 plus 500, another new object is created. 2000 plus 1000, another new object is created. So objects are created to represent new numbers. That is the reality. And this is what makes C programmers say, oh, Python is so slow, a lot of objects are created, it takes up a lot of memory. No, there are a lot of optimization that Python has. And there's a reason why objects are created in memory like these to represent numerical values, which is a topic for another session. Just hang in there. Okay. So coming back here, I told you how this works. I just put these numbers in hexadecimal format, not really these numbers, something similar to that there in the example, but it's all fine. It's all the same. It's shown in address is shown in decimal notation here. So you should know that numbers, all numbers are immutable. I'm talking about int, float, complex, bool. Bool is also a kind of a number which has just true and false, which are synonyms for 1 and 0 in Python. So all of them are immutable. Strings are immutable. Bytes is immutable. So what all objects are immutable? I told you. In Python, all numbers, all built-in numeric types, that is int, float, complex, and bool, string, bytes, and tuple are all immutable objects. I would say maybe objects of all built-in types. Objects or instances of all built-in types. That is int, float, complex, bool, followed by string, bytes, tuple, are all immutable. That's enough. You can just put it this way. Which means that once you create them, you cannot change the notion of value. Well, tuple is a very unique thing in Python. In fact, many languages still don't have them. Few of them do, but a lot of the mainstream languages I've seen, like C or C++ or Java, don't have tuples. Right. Now, the question is, what is the use of these immutable objects? Why do you need to care about it? Why do you have immutable objects in general? Immutable objects support a lot of runtime optimization. Just like in real world, The fact that you cannot really write on your currency notes, you shouldn't actually. It's now termed illegal in India to write or scratch on your currency note, right? It's illegal. You want to just use the note as they are. You can't put your signature or things like that anymore. It's immutable. You mainly cannot change the value in them. Numbers, any numbers in them. You cannot change them. They're immutable. The fact they are immutable, you can reuse that currency note across. Oh, use this term. They are fungible. Fungible. A term used with the blockchain technologies and cryptocurrencies. NFTs, non fungible tokens. But the opposite of it, they're fungible. What do you mean by that? Which means that the currency note that's with me, the $500 bill, or 500 rupees it is actually, I can give it to you for something that you sell to me. You sell me something, I'll pay you that money. You sell something for 500 rupees, I give it to you. Now, what is mine is now yours. You can use that rupee, use that money, and buy something else for your own self. And then note can exchange across hands to many people without much of a problem. Imagine a scenario where for every time money is issued, I had to print a new note, I had to print a new currency bill, right? It's not really scalable. Let's say once I get my note, the currency note, and I use it, that's it. When I have to buy something, I pay that currency note, and that note is then destroyed. Let's assume that note's lifetime is finished. Again, a new note must be printed. Then it's not very scalable. But examples like this is one thing I can think of is movie tickets. Movie tickets. If I'm booking for a movie today for today's show, it's valid for today. I can't use it tomorrow. I have to buy a new one. That bill that is given me, that movie ticket. These days it's all on the phone. In India, it's all on phone. But once upon a time, you used to get this small bill that represents a movie ticket. These are things which are like non-fungible. That means you cannot really recycle them. You cannot recycle the ticket. It's for that instant. It's done. Right? In a way, you don't have that kind of a thing in immutable objects, which means it's more beneficial. You can recycle the objects. And Python does that. Let me give you some interesting feature here. I use deliberately numbers like 1000, 1001 to be very cautious, but I'll show you with small numbers. Let's consider this. I say A is equal to 1000, B is equal to 1000, C is equal to A. A is equal to 1000, B is equal to 1000, C is equal to A. I'm going to print ID of A, ID of B, and ID of C. Well, as you can see, the object's identity of A and B are different. They are different because there are two instances of 1000 created. There are two objects with the same value, 1000 created in memory. There are two copies of 1000 in memory now. There's one copy in one location of memory, A refers to it. There's another copy of 1000 in memory, B refers to it. But when I say C is equal to A, you know that assignments copy references, which means that C points to same object as A. So A and C refer to the same object, therefore the ID of A and ID of C are the same. This is proof to show you assignments copy references. But when I create an object in the right hand side expression by using literal notation, we saw a new object is created every time. So if I have a large program and I have A is equal to 1000, B is equal to 1000, C is equal to 1000, D is equal to 1000, if I have 1000 all over the place, but every time I'm using that literal notation 1000, new objects are constructed. New objects are constructed. And these objects will be destroyed or freed from memory when they're no longer needed. That is, when there are no more references to them. When those variables lose scope or they are deleted, these objects can get garbage collected. I sort of talked about garbage collection in my earlier sessions. Now consider this. Try the same exercise. Maybe with A is equal to 100, B is equal to 100. Not 1000, just 100. Try running it. Interesting. A, B, and C are all having the same object's identity. How is this? How is this? Well, here's an interesting aspect about Python's implementation. And these are implementation details that can change over time. I should warn you that. You should not rely on these features in your code, but it's just things to know about. Maybe you can pass an interview, right? So if you can pass interviews, if it's done by people like me, it's like to show that, oh, you know a lot about Python, right? What is this? Python optimizes numbers between, I would say that numbers between -5 to plus 255. -5 to plus 255 are pre-constructed by Python runtime. Pre-constructed. What do you mean by that? You don't have to create those numbers. Those numbers are all created beforehand. So objects representing -5, -4, -3, -2, -1, all the numbers all the way to 25, they're pre-allocated and kept aside by the Python runtime, even before your program begins to run, as soon as the runtime is initialized. This is also called as interning. Interned. That word is used, intern, which means caching. It's some kind of cache. We also call these a small number cache or small number interns. So they are small numbers, right? From -5 to plus 25. So if you try to do this, if you try to say A is equal to 100, B is equal to 100, or C is equal to 100, instead of creating multiple copies of object 100, there's just one copy in memory, and all these three variables refer to them. The advantage of this is, you know that number 100, it's immutable. You cannot change it. It doesn't matter how many people or how many references you can have on them, you get this optimization. But you might now ask me, why only up to 255? Why not to 1 million or 4 million? Obviously, every single instance of number takes up memory. You can't just take all over the place. You cannot put just numbers all over the place. Your Python runtime will use up all your computer's memory just to store numbers and no space for your code. You don't want that. So they have sort of figured out that numbers in this small range is most frequently used in practical scenarios. It's very common to say a plus is equal to 5, a minus equal to 1. These kind of numbers are more frequently used. And these frequently used numbers, which are these small numbers, are alone interned. Maybe in the future, I'm not sure. Maybe there could be an implementation where they say, oh, let's also intern magic numbers, like say all 2-power numbers, like 1024, 512, 256, and 65535 or 65536 and so on. Maybe, but that's not the case today, as of now. As I told you, these are all implementation specifics in Python. But these kind of optimizations possible on immutable objects. Even strings have this kind of optimization. I'll show you that. This is an interesting one. I thought a couple of you should have tried it out and wondered. Let me show you this. A is equal to, this is a test string. And try B is equal to, this is a test string. Print ID of A and ID of B. They are different. They're different because there are two different strings created in this case. But try this out. Instead of making this string, this is a test string, let's make it a smaller string right now. Let's call this hello world. And also use hello world here. Even now they are different. They are different, right? You can see that numbers are different. You can see that one of the strings ID is 7216, another one is 2336, obviously. They are two different string objects. But imagine when I do this, where I don't use hello space world, but I use hello underscore world. And then, if you run this, they both end up magically having the same ID. The size of a string doesn't matter, by the way. Up to a string up to 4 kilobyte, I checked last. I really checked it, right? If you have a string, even up to 4 kilobyte, it's like 4,000 bytes around, right? Or 4,000 characters, 4,096 characters. And a string is only made up of alphabets, numbers, and underscore, and no special characters. No space, no hyphens, no comma. No other special characters. It should only be made up of alphabets, numbers, and underscore. These are called as word characters. Characters that make up a word. This is a word, right? Strings like these are also interned by Python when created the first time. When I create the string with this data as hello underscore world for the first time, Python realizes there are no other special characters in here, so it creates it in its own string interns. It has its own bin, let's say, in memory. It just represents it there. It's like a dictionary. It maintains an internal dictionary, perhaps. It just maintains a copy there, right? The string is kept there, and the reference is written. When I try to create a string again, when I use a literal syntax again here with hello world, before Python goes ahead and creates the string, okay, the string is only made up of alphabets, numbers, and underscore. It checks whether a string of the same data is created in the word intent cache. If it's found there, it's just going to return the existing reference. So word strings are made up of words, a single word. Just a single word. Even if you have a long string but it's not having any spaces, technically it's a word, right? So it's made up of letters, numbers, and underscore. Word strings are cached the first time they're created, and the same string is recycled across or reused across for multiple definitions. Now you might ask me, why didn't they do it for hello world? Or, the size of the string is same. Whether you put a space here, whether you put underscore, the length is same. This is not intern, but why this? The rationale behind it. You know that all variables that you create, all identifiers that you use in Python, whether it's called a, b, print, type, int, float, complex, tuple, all of these are identifiers. Ultimately, they identify things. These identifiers act as keys in a dictionary, in a namespace dictionary, which I talked about in my topic on modules. All global variables live in a namespace dictionary. Now, because it's all living in a namespace dictionary, and it's possible that you can have multiple objects. Multiple objects can be created with similar identifier names. Imagine for a while that I have one object called person, which has got an attribute called name, and I have another object called employee, which has also got an attribute called name, and I have another object which is, let's say, a laptop, and that also has a name. The attribute called name is repeated in different objects. Rather than having duplicate copies of a string whose value is name in memory that act as identifiers, they'll just have one copy. There's just a kind of a practical optimization that is inherent in Python. So these are implementation specific. Let me warn you that it's not something that's like written in the rule books and say this is a feature in Python and this will remain in all implementations. No, it's not a Python standard. It's implementation specific, which is found in the official Python and many other implementations that are sort of taken from official implementation. So this is something to know. And all these kind of optimizations are possible if an object is immutable. Interning, right? One of the optimizations is the ability to intern or cache them. You can reuse this or recycle this object because you don't have to worry about things being modified inside it. Right? Back in the days, I remember when I was young, in India, buying textbooks for your studies was a quite expensive thing. And a large part of India was in the middle class segment. We don't have a very high income at that moment. When I was young, I lived through that phase, and I think many of my friends are the same. So normally buying a textbook is a very expensive affair when I switch to new classes in school. So what we normally do, we recycle textbooks. I get a textbook from my senior who has just graduated or moved to the upper class and higher studies, and his old textbooks, I would use them. I would read it. When I'm done, I pass on the textbook to somebody else. And this works very well as long as I don't scribble on the textbook or mess it around or tear some sheets in it. Yeah. If that's done, nobody will want to take it back from me. So it's like an unwritten rule that when I'm given new textbooks, I believe that I have to recollect the cost of this textbook once I'm done. So I will not write anything on that textbook. Maybe I'll use a wrapper and put my name there when I'm using it, but after that, I'm not going to make any highlight, mark, anything as such. Maybe highlight something which is useful for the others, fine. Or make notes, fine. But that's the practical thing. But in reality, you keep the textbook in pristine format so others can use them. I think in some countries, I think toys. I know my brother lives in Australia, and sometimes kids' toys, rather than buying all these toys from afresh, you could go to some of these places where they give you those toys which you could use when the children are young, and once they grow old, all these toys can be given back to them, that can be recycled back to other kids, of course, after they're being sanitized, of course. So this is a kind of reusability that's there, right? Or reusability of objects. And you can do that if the objects are immutable. That means you cannot change them. If I got a toy and if I completely mess it up completely, you cannot go and give it back, right? So this is what it is. It's recyclable, right? So immutable objects are very easily recyclable across, and that's one of the advantage. That's a major one. The second advantage, which is got to do with concurrency, it's a very important one though. What is concurrency? I would say that your code that you're writing right now, all of this code is like having a sequential execution. Statements are executed instruction by instruction in an appropriate sequence. But when I say a code is concurrent, you can't assume a code is purely sequential in nature. They're concurrent. Maybe I do step 1, followed by step 2, followed by step 3, followed by step 4. 4 different steps, 4 different statements, let's say. But maybe step 2 does not depend on step 1's completion. It's possible. Step 2 does not depend on step 1's completion. They're independent. You can sort of make them concurrent. Rather than running them one after another, you can make them concurrent. There are multiple ways you can do that. One, you can have threads of execution or multiple CPUs, parallel processing and all that, where you can have 2 different set of statements running in parallel. All that can be done. That's one way. Else, you can have very elegant algorithm. Maybe step 1 is causing some delays. I'm trying to hit a request to a website, and for the time I could get the response, there's some delay. Obviously, internet latencies, right? And these delays, the CPU need not have to be wasted. You could use the CPU to run something else when this is still ongoing. I send a request, until I get back a response, I can do something else, right? That's concurrency for you. So when you have concurrent code, it's possible that multiple concurrent code can sometimes go and access the same data. It's like one particular code manipulated some data and went for a request, waiting for a response, and then you moved over and ran some other code path, and that code path tries to use the data. That's a problem. It's a concurrency problem. You need to somehow say that, oh, the old code that comes back should have expected that data to be in the old state, what it was expecting, but that could have been manipulated by another code path. It's a mutual exclusion problem, we call them in threading world. Now, immutable objects are completely concurrency safe. If an object is immutable, you cannot change it, you cannot modify it. There's no way of changing things. You can read it. Any other thread or any other concurrent code can also read it. So you don't have to worry about using locks or mutual exclusion patterns to access them. There's no need to synchronize when you're dealing with immutable objects. They are fairly advanced things. I hope to cover that in more depth in my advanced Python training sessions, which is after this Python this programming from the very basics. I'll be doing advanced Python trainings where I will cover that in more depth. But something to know about, immutable objects are automatically concurrency safe, and that's the reason they exist in Python. There are some languages which treat all data as immutable, all of them. I know, for example, Lisp, Haskell, and a couple of other languages. They don't have mutable data types. They have everything as immutable. Everything is immutable there. The concept of mutability is like scary for them, right? But Python is a practical language. There's a Zen in Python that says, although practicality beats purity. If you really want to live in a world that's where everything is immutable, I give you immutable objects. It gives you some immutable objects. You got to live with it. But if you think you need mutability and you're okay to worry about synchronization and other things, you don't care about reusing that data, then you have mutable objects available for you. So it appeals to both words, right? That's what this is all about. All right, this session stretched a bit, and I think this session had a bit of interruption, which I will be, knitting it together. A little bit of editing work done in this session, simply because there was some drilling work going on in my neighborhood. So there have been some stops in the midst. Anyways, I hope you won't notice that, as hopefully when I edit it. I hope you found this session useful. You learn about the tuple, all the things you can do with the tuple. In the next session, I will tell you about interesting features related to tuple and introduce you to a list. So these features are not tuple specific. These are like common sequence operations, which I'll talk about, common sequence operations, and then I'll introduce you to a list. And I'll tell you about all the different things you can do with a list in the next session. I hope you like this video. If you do like this video, do hit the like button and do subscribe if you're not already subscribed, if you want to watch more such videos, which will come up to your notification. And I hope to see you in the next one. Thank you very much.